Good morning, good afternoon, everyone. Welcome to Keysight Technologies virtual event series. We are pleased to have you here for today's virtual event on test and validation of Terabit designs with state-of-the-art digital characterization tools. My name is Girish Baliga from Keysight Marketing, and I am the moderator at today's webinar. And also, I will be presenting this session. Today, we'll be spending the next 45 minutes or so deep diving into test and validation of Terabit designs with state-of-the-art digital characterization tools. Before we get started, couple of housekeeping inputs. During the presentation, you can dial in your questions in the Q&A box on the streaming console. We'll be more than happy to answer your questions and get back. Also, please share your recommendations on the survey form, which will appear as a pop-up during the course of the virtual event. There is also research collateral on test and validation of Terabit designs with the state-of-the-art digital characterization tools on the webinar console. Please feel free to download these from the resource list. In addition, please share your comments about the program to enabling us to serve you better. And please use audio headset or earphones to listen to the virtual event audio for good audio effect. I'll be presenting today's paper on test and validation of Terabit designs with the state-of-the-art digital characterization tools. At Keysight Technologies, I am part of the marketing department and manage the marketing for wireline and high-speed digital, 5G wireless, aerospace defense, and software business. Without much ado, let us begin this session. The overall data center infrastructure and hyperscaler market is growing quickly. By year 2024, it is estimated to grow to around 90 billion US dollars. Part of that growth will be from the market, which is going to serve both the data center and the hyperscaler, which is expected to grow to around 12 billion by the year 2023. The data center infrastructure is constantly evolving. Emerging technologies such as 5G, including FR1 and FR2, artificial intelligence, virtual reality, machine learning, Internet of Things, and autonomous vehicles generate explosive amount of data in the network, thus creating new computing and performance demands in the data center. There are six key trends which drive the computing, data center, and hyperscaler industry. Let's have a look at each of these in greater detail. The overarching driver in the communications ecosystem is the obvious data explosion and thus leading to enormous data growth. When we take a pick of industry reports, we see that different reports highlight and point to a region and which shows that the explosion of data growth is very, very clear. As all of us know, it was not too long ago that voice traffic dominated communications traffic. But now we know that it is video, virtual reality, autonomous driving, and a host of new Internet of Things or IoT applications and sensors, which is going to drive growth. Therefore, data is exploding and it is getting more and more mobile and will continue to grow exponentially. On the flip side, the total operator capex and opex spending on the network infrastructure to support all of this is flat or declining. Price points of any new infrastructure flowing into these environment are quickly commoditized, and price points are driven down between 20 to 30% a year. To handle this challenge, the operators, the service providers are increasingly applying data center and cloud network principles and topologies. These principles involve moving functionality into software through SDN and NFV, and leveraging bare metal servers and cloud compute to scale with the data center economics. That has been true for the core network already, but exactly the same virtualization is coming to the radio access network with the move from 4G to 5G. The impact to major wireless infrastructure vendors is huge. Previously, the bulk of the business was proprietary hardware platforms with large custom ASICs and nice profit margins. It's not so anymore. Their customers are forcing them to leverage standard compute platforms, become more open, much cheaper, and dynamically reconfigurable. And now NEMs, or the network equipment manufacturers, are in a revolution with 10x to 50x magnitude cost reductions. In addition to these industry challenges, there are many other significant factors. New technologies need faster speeds. For example, to reach speeds of 400 gig, 800 gig, and terabit speeds in the data center and the hyperscaler, pulse amplitude modulation, or PAM technology is needed to effectively double the data throughput of NRZ signaling. Data transmission is expanding to low volume niche applications, as well as long haul networks, where performance is also very, very important other than cost, and also for very high volume applications, like I mentioned, such as metro networks, data center interconnects, and even access networks. Last but not the least, new standards such as Gen Z and CCIX are being introduced to applications that are tailored for specific tasks. The challenge of developing and introducing these new technologies is significant, and it is also expensive. The whole world is connected, and the pace of communications innovation is accelerating as end users demand faster, more responsive, and more reliable connections. As I mentioned earlier, communication links are both wired and wireless, covering everything from Ethernet, optical fiber, cellular wireless, and other wireless data communications such as Wi-Fi. Test increasingly needs to span several of these domains, measuring from a baseband cellular signal to a radiated over the air waveform. End to end measurements may originate from handled user equipment and to be evaluated at an internet data center. Data center infrastructure solutions need to cover all the network layers, starting from the physical layer, layer 1, all the way to the network layers from layer 2 to 7, including software defined networking, or SDN, and network functions virtualization, or NFV, validation, and traffic loading. As we move towards terabit, data center infrastructure innovations have to focus on fast deployment of new services. In a span of less than 20 years, data center speeds have swiftly evolved from 10 gig to 100 gig and soon into 400 gig and now are into terabit throughputs. Each new speed class built off the previous generation, but is limited early on by high cost and constrained demands. For example, when 100 gig began deployment in the data center in 2014, the full manufacturing build out only became cost effective in the last couple of years with the introduction of more efficient transceiver modules. No sooner did data center operators move into the rapid deployment of 100 gig that they needed to start planning into 400G, 800G, and now into terabit throughput speeds. Researchers have already begun working on 1.6 terabit and beyond. At the core of every network upgrade is the transceiver, and at the core of every transceiver is the channel capacity. Traditionally, data center operators tend to upgrade their network architecture every couple of years. However, many data centers are currently at maximum capacity, and data center operators need to find a way to increase their channel bandwidth to reach terabit speeds as cost effectively as possible while ensuring interoperability of devices from different vendors. The move from 100G, 400G, 800G, and now into terabit throughputs in the data center is revolutionary and not evolutionary. Optical transceivers, like I mentioned before, will need to use advanced signal modulation and coding to reach terabit throughput speeds. These techniques create new test challenges for the transceiver manufacturers. Data center operators need to increase channel capacity as they transit from 100 gig, 400 gig, 800 gig, and now into terabit data throughput speeds. This can be achieved with the optical transceivers, like I mentioned earlier, that use advanced modulation and coding techniques. Up to data rates of 100 gig, NRZ or non-return to zero was the most common signal modulation scheme. However, as speeds of NRZ designs increased above 28 gigabit per second, channel loss became a limiting factor. PAM-N, or specifically PAM4 modulation, was the recommended method as data rates started moving from 100 gig to 400 gig, 800 gig, and further. However, the PAM-N or PAM4 designs are far more susceptible to noise. Therefore, FEC, or forward error correction, is used to correct channel errors in PAM4 links and must be considered in PAM related design testing. New measurements to characterize impairments that were previously not an issue in NRZ designs need to be taken care of with PAM. With the accurate and repeatable results, PAM4 interface components and systems will help accelerate the development of the systems which will get into the market at breakneck speed. As we know, NRZ signal modulation is a two-state transmission system, also referred to as a two-level pulse amplitude modulation, or PAM2. However, higher data rates require 4 lanes or more of say 25 gigabit per second or more NRZ modulated signals. Since NRZ has gradually evolved over the last 50 years from data rates from say 110 bit per second all the way to now 100 gig, 400 gig and 800 gig per second, gigabit per second, many new concepts and challenges have already been researched and addressed. Transmitted signals using NRZ modulation are received without significant errors. With the PAM or pulse amplitude modulation, or specifically PAM4, it uses 4 amplitude levels to represent a symbol and effectively doubles the data rate or throughput in the same bandwidth as NRZ. However, like I mentioned earlier, PAM4 designs are far more susceptible to noise since an amplitude swing of 2 represents 4 signal levels. As a result, the SNR or signal to noise ratio is lower, and analyzing noise in transceiver designs becomes a very critical factor. Like I mentioned earlier, forward error correction or FEC is integrated into the transmitted PAM signal so that it can be received without significant errors. Optical transceiver manufacturers must design and test so that they ensure that transceivers have a strict compliance with the defined specifications and are interoperable with the other network components and transceivers from different vendors. Network downtime due to faulty transceivers is not an option for data center operators who have a guaranteed SLAs or service level agreements with users. At the end of the day, we need to ensure that the best of testing is done so that it ensures a fault-free 24 by 7 by 365 days operation at data centers. Like any new technology, the price of new transceivers would tend to drop sharply after introduction to the market, and development costs are amortized as the volume ramps. Next generation transceiver technologies like for terabit speeds will reach mature pricing within a couple of years of introduction. At maturity, the cost of transceivers is directly proportional to the complexity of the design and the number of components in the system. And the test times also contribute significantly to the overall transceiver cost. More efficient testing of a broad range of transceiver data rates would accelerate innovation and would lower the cost. The process begins in the research and development phase with the designer of transceiver components that would continue to the design and validation of the transceivers and then through into manufacturing tests. At each phase of the product development cycle, the test solution should be rugged so that it gives a first time right test results that can be used to maximize test efficiency. Test tools should help you shorten design cycles and dramatically improve productivity, thereby ensuring quality and significantly reducing overall costs. With the terabit transceiver technology squarely on the horizon, data center operators are also looking for new ways to design and operate their networks to withstand the kind of traffic that billions of devices will generate. One of the key aspects on this front is the SDN going mainstream as well as networks becoming autonomous. Today's fast-paced and demanding environment means the designers have much less time to understand the intricacies of the technologies they are testing. Each new speed class and every generational change of industry standards would put new risks in their path, such as signal integrity issues. The best in class test solutions should help to test their high speed digital designs across all product development stages, from design and simulation to analysis to debug and compliance test. It should ensure that these tools will help anticipate test challenges, optimize performance, and also help accelerate and help mitigate the risks so that one can time to market their next generation high speed digital designs. So in summary, we are all aware that the world is still experiencing a very high growth of internet, and that's coming mostly with the higher transmission speeds. So it's expected that this growth will be by a factor of 3 or more in the next half a decade. And interestingly, 99% of the traffic is originated in the data center or terminated in the data center itself. So the challenge for the customer is to keep up with the pace of switching technology at the data center. This is a key parameter that will determine the traffic data center can handle. Another challenge is striving to reduce the cost per bit and also the power consumption while increasing the throughput. The introduction of new standards will enable new generation technologies like optical coherent transmission technology, which was initially used in long haul transmission, and that would evolve into metro networks and expand into the data center. Significantly faster data transmission rates and greater levels of spectral efficiency can be achieved using higher order quadrature amplitude modulation or QAM signaling. Transceivers need to densify electronic and photonic integration with the tighter specification and performance margins for all the components. One needs to reduce the size, cost, and power consumption of their transceivers. On that front, there are various aspects which need to be taken care of, whether the test is going to be a transmitter, receiver, device, and so on and so forth. For the transceiver test, telecom and datacom transceivers using coherent transmission technologies are optimized based on reach, spectral efficiency, and power consumption. To ensure optimization, one needs a flexible and scalable test solution for the analysis of dual polarization in phase and quadrature IQ signals. Performing common measurements such as EVM or error vector magnitude, IQ offset, IQ imbalance, quadrature error and skews is complex in optical coherent signal analysis. The selection of best-in-class test tools will help accelerate the deployment of the designer's next generation intelligent telecom and datacom networks. The next big chunk here is with respect to the terabit receiver test. Next generation transceivers would enable telecom service providers to support 100 gig, 400 gig, 800 gig, and soon into terabit applications. To thoroughly test an optical transceiver or specifically a receiver, one should stimulate it with complex waveforms using different modulation formats and data sources. It is also important to deskew and pre-distort input signals to account for any linear impairments in the test setup and measure the true accuracy of the optical receiver. The next piece, like I mentioned earlier, is to do into very high speed gigabit device testing. Electro-optical and optoelectrical components used in coherent optical transmission systems have unique test challenges. For example, to test dual polarization IQ modulators and intradyne coherent receivers, it is necessary to measure the insertion loss during transmission. To fully characterize optical coherent devices, one needs to analyze many parameters, which include bandwidth, gain, imbalances, and then group delay and skew. These measurements are complex and time consuming. So again, deciding on the right test tools will help the designers to gain first mover advantage. So it is also worth to have a look at the switching speed evolution of a data center. As we speak, we are right into this development, and we don't see a glass ceiling in the near future. Currently, 800G is starting to ramp up, but as we spoke earlier, the 1.6 terabit transmission speeds are also gaining steam. It's typically based on the 224 gigabit per second per lane rate, which has left the pathfinding phase, and the first customers have now received their first ASICs and are already starting with validation tests. The industry needs state of the art next generation test equipments to test both the transmitter and the receiver side of things. And today in the market, uh, we have to ensure that the best in class BERT or the bit error ratio tester will help provide a high quality signal that can be tested in speed classes never heard of until today. Common challenges that the test engineers are facing while moving to next generation standards, in addition to those which I mentioned earlier, are higher baud rates that mean greater channel impairments like ISI or intersymbol interference, jitter, and amplitude noise. Along with the fast evolving technologies, highly flexible testing capabilities are also required. Also, the standard compliance tests are getting more and more demanding and will consume even more resources to set up. All this can slow down the time to market and limit the revenues for the designers. So let us now dive deep and understand how these challenges are overcome as the designers move towards 1 terabit and beyond. Overcome the challenges, we have the new M8050A high performance bit error ratio tester or BERT, which will help ensure that you expedite your design and test so that you have the first mover advantage in the market. As we know, each speed class of a switching ASIC requires a full design cycle as is outlined here. The design cycle starts typically with the modeling. Based on this simulation, the ASIC is designed. When the first prototype of the ASIC or the serializer, deserializer, or SerDes are available, parametric test starts to validate the basic performance. In this phase, where parametric tests often require a highest flexibility, arbitrary waveform generator like the Keysight M8199A can also be used as an alternate to a pattern generator. Let us now dig deeper into the details of the new M8050A 120 gigabaud bit error ratio tester, or the BERT. The Keysight M8050A high performance bit error ratio tester enables the accurate characterization of receivers used in next generation data center networks and server interfaces. With uncompromised signal integrity, it supports NRZ, PAM4, PAM6, and PAM8 signals and data rates up to 120 gigabaud. With the flexible architecture of the M8050A, it supports 1.6 terabit pathfinding as well as other leading edge technologies. In addition, it supports symbol rates from 2 gigabaud to 120 gigabaud. And like I mentioned earlier, various line coding techniques, as well as it has a built-in 7-tap de-emphasis for improved channel loss compensation, as well as transition time at less than 5 picoseconds and around 100 femtoseconds, less than 100 femtoseconds root mean square intrinsic random jitter. It also has a jitter injection integrated and calibrated for receiver tolerance testing of RJ, PJ1, PJ2, BUG, SRJ, and clock by 2. In summary, the M8050A BERT with the Keysight's ultra high bandwidth UXR series 80 gigahertz scopes oscilloscope would give the designer a full 1.6 terabit receiver and transmitter test solutions to assess the designer's Ethernet system. As you can see from this particular slide, it gives an overview of the M8050A bit error ratio tester, or the BERT system. As we can see, the M8050A comes typically on a 5-slot AXIE chassis. The M8042A pattern generator, like I mentioned earlier, is the most advanced pattern generator you can get on the planet today. It offers 2 to 120 gigabaud NRZ and PAM4 pattern generation, all with outstanding signal integrity, as you can see. As you can see from the screenshot of a 120 gigabaud PAM4 signal on the right side, you can see a very nice signal with outstanding signal integrity. The remote head supports baud rates up to 64 gigabaud and also can be extendable to 120 gigabaud with the licenses. The pattern generator with its 7-tap de-emphasis supports conformance test according to the IEEE 802.3 CK, where an emphasis with the 3 precursors is required. Another benefit of having more taps for de-emphasis is to have a lower distortions at the output due to the better channel match. The differential output voltage at the remote head is 1.4 volt peak to peak. Like I mentioned earlier, the M8042A is not just limited to NRZ and PAM4. It also provides options for PAM6 and PAM8 pattern generation. Various line coding and baud rate combinations are currently under consideration, like the PAM4 with 112 giga baud, PAM6 with 90 giga baud, or even PAM8 with 75 giga baud. Most likely, various flavors will make it depending on the distances a signal has to travel from one device to the other. This can be challenging if one does not know today which line coding one is going to be using down the line at a later point in time. So flexibility is very important, and that particular flexibility is provided with this pattern generator. The M8050A along with the various bundles would support PAM6 and PAM8 on pattern generator and on error analysis. Now let's have a deeper look into the details of the clock module. Each pattern generator requires a clock module for operation. The clock module can provide 2 to 60 gigahertz clock, as you can see from the slide here, to create the 4 to 120 gigabaud at the pattern generator output. With an intrinsic jitter below 100 femtoseconds, this is the cleanest clock for a bit error ratio tester you can get today. This provides enough test margin to emulate noisy signals for all types of high frequency jitter one can envisage. 8050A design goal is to be open for implementation of future hardware features, as well as to provide the technology for customers to support from development, from pathfinding to conformance test. We invest a lot to develop our own ASICs and the own RF components that would allow us to optimize the ASIC for the desired requirements of the instrument. The memory FPGA and DAC based design provide the maximum flexibility which one can get from the bird. The biggest thing today in hardware is scalability and upgradation, and the M8050A provides the user with all that flexibility so that they can change their application, upgrade, and also helping save real money in the long term when they would like to invest in a new M8050A platform. In summary, the Keysight Technologies M8050A high performance bit error ratio tester, along with the UXR ultra high bandwidth oscilloscope, enables accurate characterization of transceivers used in next generation data centers, hyperscalers, and server interfaces. With the uncompromised signal integrity and support for NRZ, PAM4, PAM6, and PAM8 signals, and for data rates up to 120 gigabaud, the flexible architecture would help support 1.6 terabit data rate pathfinding, as well as for other leading edge technologies. Thank you, participants, for participating in today's virtual event. On behalf of Keysight Technologies, I would like to thank you all for taking time out and participating in today's virtual event. Like I mentioned earlier, please take time out to enter your requirements on the survey form, which will be shared to you at the end of this virtual event. Dear participants, we hope this session was helpful to you. This session would also be available on demand shortly so that you can go through this virtual event again. We would like to thank you for participating in this session. Keysight Technologies runs a series of virtual events periodically, and we will keep you posted on the next set of virtual events over email and other mode. As I mentioned earlier, this virtual event will be available on demand, and you will get an email once it is ready at the address you would have used for registration. You can view this virtual event any number of times on demand. Also, you can share the on-demand details with your colleagues, team members, friends, etc., enabling them to register and participate. With that, we would like to sign off this virtual event. All of you have a nice day. Thank you and bye.